This is section 6.4, and we're going to be talking about first order linear differential equations. Okay, now these equations occur in the form, and this is the form we want to get them in, of dy dx plus some function p of x times y equals q of x, where p and q are functions only of x. Okay? And our solution occurs in the form y is 1 over some function u of x times the integral of q of x times u of x dx. U of x is called our integrating factor. And u of x equals e to the integral of p of x dx. So here are the steps you need to follow to do this. Number one, of course, is whine, cry, and complain. Number two, you want to identify p of x and q of x. The next thing you want to do is integrate p of x, and then you find your integrating factor, this u of x, then will be equal to e times, which is our result from step 3. All right, once you've done that, then multiply and simplify. Q of x times this integrating factor u of x. Then you integrate results from step 5. And finally, you plug in and simplify. This gets you a general solution, and if you find a particular solution, then you plug in the initial points. Okay. Let's work some examples. This will be an easy example. Dy dx plus 1 over x times y. This is usually see this written as y over x, but they broke it out to be nice. Equals 3x plus 4. All right, so step 1, we need to find p of x is going to be 1 over x, and q of x is 3x plus 4. In other words, this whole thing over here is our q of x. All right, so now we come in and we need to integrate p of x. So I'm going to integrate dx over x, which you should recognize as the natural log of x, So my u of x then is e to the natural log of x, which is x. Okay. So far we're in good shape. We've got our u of x, so now we need to do our q of x times u of x, which is going to equal to this times this. That's going to give me 3x squared plus 4x. And now we need to integrate. We have 3 times the integral of x squared dx plus 4 times the integral of x dx. Remember on this one, this is a simple rewop. Add 1, which gives us 3. Divide by that, so 3 over 3 is 1. Plus, this gets us x squared over 2. 4 divided by 2 gives us 2. And then plus our integrating, our constant of integration that we put out here. All right, so we've got this now. Now we can come back over and write our solution. Remember, our solution is the form of y equals 1 over u of x times the integral of q of x, u of x, dx. So we know what u of x is. It was x, so it's going to be 1 over x times, and then this guy we just found here, which is x cubed plus 2x squared plus c. And then I divide my x in on all of them, which gives me x squared plus 2x plus c over x. And there is our solution. Okay, let's take another easy example, but one which has more algebra in it. So we have y plus 1 times the cosine of x dx minus dy equals 0. All right, now first thing we notice is I've got these things, so we're going to divide through by dx. And it gives me my dy dx, and that's still 0. It's cosine of x. Now, you notice I've got my y tied up in here with this, so what I have to do now is distribute. So I'm going to end up with y times the cosine of x plus cosine of x minus dy dx equals 0, and I want this in front, so I'm going to end up with a minus dy dx plus y cosine of x equals negative cosine of x. And I move that over here. Now, we've got a negative here, which is what we want. And the trick to this is if you get anything in front of dy dx, you have to divide it into all the terms. So in this case, I'm going to divide everything by -1, which just means I'm changing all my signs. Minus y cosine of x equals cosine of x. So now we can start then on step 2. So my p of x is going to equal to a negative cosine of x, because I've got a minus here and our form had a plus. And my q of x is cosine of x. So now we have to integrate p of x, which equals negative the integral of cosine of x dx, which equals negative sine of x. Okay, so now we're ready to come back in, and we're ready to do our integrating factor, which is u of x going to equal to e to the negative sine of x. All right, so now we multiply u of x times q of x, which is cosine of x. So I'm going to end up with cosine of x times e to the negative sine of x. There's nothing I can do to simplify this, but we have to integrate this thing. And you think, I don't know how to do this, but you do. This is a simple u sub. U is negative sine of x, so du is negative cosine of x dx. So now I've got the cosine of x dx, but I don't have a negative. So I'm looking at negative the integral of e to the u du, which is negative e to the u, and I plug back in for my u. So my integral of q of x, u of x, is going to equal to negative e to the negative sine of x plus c. And we want to add our constant integration out there rather than multiply it out in front. Okay, so we've got that pretty good. Now we're ready to plug it in. So here's my mu. So y is going to equal to negative 1 over hang on. Sorry. 1 over, it's not a negative, it's just a 1. Because my mu of x is, mu of x here is what I'm after. So it's going to be, since this is e to the negative, we go to 1 over, means we just change the sign of this. So it's going to be e to the sine of x times our result here, which is a negative e to the negative sine of x plus c. And now we distribute on through. When I multiply these together, you notice I've got a sine x and a negative sine x. So that just becomes e to the 0, which is 1. So y then will be equal to a negative 1 plus c e to the sine of x. And there is our general solution. All right, let's do another one. And this one kind of comes back and looks at what we've already done. So let's take a look at dy dx plus y over x equals 0. Now, if you look back at the first example I did, you notice this is very similar, except we had something over here. Now, if we look at this, our p of x would be equal to 1 over x. Our q of x is 0. Now, what we can also do, if we take a look at this, this is a classic separation of variables problem. So I have a dy dx equals to negative y over x. And now I divide over, so I'm going to end up with a dy over y equals negative dx over x. This is cross multiplication. Now you notice I'm not using any of these. You can plug it in if you want, but what's going to happen, the q of x, which is 0, times our u of x, and let's go ahead and do this. Let's find our u of x. So the first thing we need to do to find our u of x, if you remember, is to integrate p of x dx, which is the integral of dx over x, which is natural log of x. So u then is going to be equal to e to the natural log of x, which is x. All right? And if you actually take a look at this, what's happening is that our q of x times u of x equals 0. So all we're left with is basically what we started with, okay? We knock this thing out. So we're left with basically just this 1 over x, which is what we had to begin with, all right? And we do this with a separation of variables. And so when we integrate both sides, I end up with the natural log of y equals negative natural log of x plus c. I'm going to add this over, natural log of y plus natural log of x equals c. And there's a log law which says when you add outside logs, it's the same as multiplication inside. So this gives me a natural log of x times y equals c. And I raise everything to the e, so e to the natural log of xy equals e to the c, or xy equals e to a constant is just another constant. All right? And so there's our solution. Now, this is one where we had to come back in then and so our solution ended up with xy equals c. And we need to find the solution at y of 2 equals 2, or they may give you 2, I don't remember. So we just plug in. So my x is 2, my y is 2, equals c, so c equals 4. So now what I'm going to have is x times y equals 4, and if I solve for y is going to be 4 over x. And there is our particular solution to this guy. And you notice that it's irrational. Okay, for this next one, I need you to get your books out, please, and take a look at word problem number 39. I don't want to read all of this, but you might want to pause this and read this, because what I'm going to go through now is to actually look at this thing. So part A, we had to write a differential equation. Now what we know is that the total rate of change of glucose in the body, and I believe it was glucose they're putting in on an IV, is going to equal to the rate of glucose being put in to the IV minus the rate of glucose out. All right, so what we know then is this is going to be dq dt, and we're going to change these things here in just a bit. So the rate of glucose in is little q minus, and this is where it's proportional to the amount that's in there. So it's going to be k times q. Now you notice we've got a lot of q's in here, and we're getting ready to do this when we come out. But let's go ahead and take a look at this. We'll rewrite this now as dq dt plus kq equals little q. So what I'm going to do is I'm going to let y equal the q in this problem. So let's rewrite this as dy dt plus ky equals little q. And now if you go in and take a look at this thing, you can see what's going on with it. So our P of t in this case is going to be k, and our q of t, which is different from this other one, that's why I changed it. This is from the linear one, is going to be little q. So the first thing we need to do then is integrate our p of t dt, which is k times the integral of dt, which is kt. So our integrating factor, u of x, is going to be equal to e to the kt. Okay, so that's good. Now we need to do our q of t, and this is this one up here, times, this is u of t, which is going to equal to q times e to the kt. And remember, little q is a constant, if you read on the problem. Q is the rate at which glucose is being put in on the IV, and you sure hope that's a constant, that they're not changing, that this doesn't change with time. Okay, so now we're ready to go in and plug in what we got. So y, no wait, first we need to integrate. Got ahead of myself. So we need to integrate, and q comes out because it's a constant, e to the kt dt. Here again, I've got u is kt, du is k that I don't have, so I'm going to have to divide by k. So when I integrate this thing out, I'm going to end up with q over k times e to the kt, and then add our constant out at the end of this thing. So now we're ready to come back in and actually write our solution. So y equals to my u of t, which was e to the kt, and it's 1 over that, so it will be e to the negative kt, times my integrating that I've got here, which is going to be q over k e to the kt plus c. So this is slick. And then I distribute on through, so y is going to equal to e to the negative kt times e to the kt will give me e to the 0, which is 1. So I'm going to end up with q over k plus c times e to the negative kt. All right, and we're given an initial condition. The first thing I'm going to do then is, remember we substituted y for q. So let's go back in and resubstitute in. Q now is equal to q over k plus c e to the negative kt. And when t equals 0, my initial condition, q equals q0. So we plug back in. Have q0 is going to equal to q over k plus c times e to the 0, or q0 is q over k plus c, and I solve for c. So c is going to equal to q sub 0 minus little q over k. And remember, k is the rate at which the body is metabolizing this. It's our constant proportionality. So now we plug back into our original one. So q is going to equal to q over k plus, now my c is q sub 0 minus little q over k times e to the negative k t. And this constant here depends on the body type and metabolism of the individual that you're putting this IV in on. Okay, so that gives us then part B. And finally, we need to go to part C, which is finding the limit as t goes to infinity. In other words, what happens if we let this go on and on and on forever? What happens is poor dumb slob. So the limit of this is going to be limit of q over k plus q0 minus q over k times e to the negative k t. Okay, because this term does not have t in it, we pull it out of the limit. So I'm going to have a q over k plus, these are not a function of time. I'm going to have a q0 minus q over k times the limit as t goes to infinity of e to the negative k t. All right, now, important thing to remember, e to the negative infinity is 0. So this whole term here, when I plug t in, I get infinity, goes to 0. So the limit then, as t goes to infinity, is the rate at which it's going in divided by the body metabolic rate. And this will give us the amount that, or at least what this thing should approach as time gets big and as we go on. And so that is your answer to all of these things. This will be working for 2 assignments. And be sure to come back in and get all of this stuff down as well as you can.